The derivation of Lagrange's equations, as typically introduced in the study of classical mechanics, often stems from a consideration of the instantaneous state of the system. By analyzing small virtual displacements about that instantaneous state, we employ what is fundamentally a differential principle. The D'Alembert principle is prime example of this approach. It provides a localized snapshot of physics answering the question, how does system respond to infinitesimal nudges right now? However, theoretical physics offers us an alternative, a remarkably elegant and mathematically powerful perspective. Instead of focusing on a single frozen moment, it is possible to obtain the equations of motion from a principle that considers the entire motion of the system between two distinct points or times, t1 and t2. Such an approach examines small virtual variations of this entire global motion from the actual physical trajectory. A principle of this nature is known as an integral principle. Before we can formally state the most important of these integral principles, we must precisely define the mathematical arena in which it operates. We must move beyond our intuitive three-dimensional physical space and construct an abstract framework known as the configuration space. Consider a mechanical system. If the system is subject to constraint, we can define its instantaneous configuration using a set of n independent variables known as generalized coordinates, q1, q2, up to qn. You can imagine an abstract n-dimensional Cartesian hyperspace where each of these n generalized coordinates forms a distinct coordinate axis. This n-dimensional space is the configuration space. The profound beauty of this space is that the entire state of our complex system, no matter how many individual particles, rigid bodies, or linkages it contains, is represented at any given instant by a single solitary point in this hyperspace. As the time progresses, the physical system changes its configuration. The values of the generalized coordinates q1 to qn evolve continuously. Consequently, a single representative point moves through the configuration space, tracing out a continuous path. We define this path or curve as actually the path of the motion of the system. It is crucial to emphasize that this path in configuration space has no necessary geometric resemblance to the physical trajectory of any actual particles in tracer space. Every point on this curve represents the entire system configuration at that specific instance of time. Time itself is treated purely formally here. It acts as an independent parameter of the curve. To each point on the path, there is associated one specific value of time. Having defined our space, we must specify the scope of the physical systems under consideration. The integral principle we are building towards describes the motion of mechanical systems where all forces, except the forces of constraint, are derivable from a generalized scalar potential. We define or denote such systems as monogenic systems. This generalized potential may be a function of coordinates qi and their velocities qi dot and time t. If this potential happens to be an explicit function of the position coordinates only, then the monogenic system reduces to a far more familiar conservative system. For monogenic systems, we define a fundamental scalar quantity known as Lagrangian, denoted by L. It is defined as the kinetic energy of the system T minus the potential energy. With configuration space defined, path of motion understood, the Lagrangian established, we are ready to state our fundamental postulate, the Hamiltonian principle, or the Hamilton's principle. Hamilton's principle states that the motion of the system from time t1 to time t2 is such that the line integral, often called the action or the action integral, has stationary value for the actual path of the motion. Mathematically, we define this action integral as following. Let us rigorously unpack what stationary value means in this context. Out of all the infinitely many mathematically possible continuous paths by which a system could travel from its starting configuration at time t1 to its end configuration at time t2, nature dictates that system will actually travel along that specific, unique path for which the value of the action integral I is stationary. By stationary, we mean that if we calculate in the integral along the true physical path, it yields the exact same value, 2 within first order infinitesimals, as the integral evaluated along all infinitesimally neighboring virtual paths. These neighboring paths differed from the true path only by infinitesimal virtual displacements, but importantly, they must all start and end at the same fixed configuration at T1 and T2. The variation at the endpoint is strictly zero. We can summarize Hamilton's principle mathematically with a single incredibly compact equation. We state that the variation of the line integral I for fixed time T1 and T2 vanishes. Here we have explicitly written the Lagrangian L as function of n generalized coordinates qi and n generalized velocities qi dot and time t. The del operator represents a virtual variation, a comparison of true path against fictitious neighboring paths occurring in exact same time interval. If systems constraints are holonomic, meaning they can be expressed as algebraic equations connecting the coordinates and time, thereby allowing the variables qi to be treated as truly independent, then Hamilton's principle serves as a sufficient condition for deriving the equations of motion. Instead of viewing Newton's laws as the ultimate foundation, we can take Hamilton's principle as the basis and defining postulate of the mechanics of monogenic systems. Our immediate task, therefore, is to develop the mathematical machinery required to handle this delta variation. We must turn to a branch of mathematics known as calculus of variations, which will provide us with the systematic tools necessary to rigorously extract the differential equations of motion from this single stationary integral. To develop this machinery, let us temporarily abstract away from the physics and consider the problem in essentially one-dimensional mathematical form. Suppose we have a function f of y dot and x. Here x is an independent variable and y is a dependent variable, forming a path y of x between two values x1 and x2. The quantity y dot represents the derivative of y with respect to x. We wish to find a particular path y of x such that the line integral j of a function between x1 and x2 is defined as this. And we need this integral to have stationary value relative to paths differing infinitesimally from the correct function y of x. The variable x here plays the role of the parameter t from our physics problem, and we consider only those paths for which the endpoints are fixed. The correct path and the varied paths all connect these two specific points in the xy plane. To manipulate this mathematically, we must put the problem into a form that enables us to use familiar apparatus of ordinary differential calculus. We need a way to parameterize the neighboring paths. We can denote such set of paths by introducing an infinitesimal parameter alpha, writing the paths as functions of both x and alpha. We define the path where alpha equals 0 denoted as y of x, 0 as representing the correct path we are trying to find. We can then construct a parametric family of varied paths using an arbitrary auxiliary function eta of x. A possible set of varied paths is given by following. For simplicity, we assume both the correct path and the auxiliary function are well-behaved, continuous and non-singular between x1 and x2, with continuous first and second derivatives. Crucially, because all varied paths must pass through the fixed endpoints, the variation must be zero at those endpoints. This strictly requires that the arbitrary function to vanish at points x1 and x2. For any given parametric family of curves defined by eta of x, the integral j is no longer just a function of the path, it becomes a function of the parameter also. The condition of obtaining a stationary point for the integral now reduces to the familiar condition from the ordinary calculus. The first derivative of j with respect to alpha evaluated at alpha equals 0 must be 0. We differentiate under the integral sign. Since the integrand f depends on alpha through both y and y dot, we must apply chain rule for partial derivatives. We must now manipulate the second term in the integrand. Notice that the y dot is derivative of y with respect to x. Therefore, the order of differentiation in the second term can be swapped. This allows us to isolate the del y by del alpha term. Consider just the integral of the second term. We can integrate this by parts. Let u be del f by del y dot and del dv equals to d by dx of del y by del alpha dx. Integrating by parts yields us the following. Now closely look at the first term on the right hand side, evaluated at the boundary. The condition on all varied curves that pass through the endpoints must be implemented. This means that the partial derivative of y with respect to alpha at x1 and x2 must vanish because eta of x vanishes there. Therefore, the evaluated boundary term is exactly 0. Substituting the remaining integral back into our expression for dj by d alpha, we can factor out the common term also to reduce us to this equation. We now invoke a profound piece of logic. The partial derivative del y by del alpha occurring in this equation is directly proportional to our arbitrary function eta of x. Aside from continuity and endpoint conditions, eta of x is completely arbitrary. There is a fundamental lemma of the calculus of variation which states that if integral of the form integral over m of x eta of x t of x is 0 for all arbitrary functions eta of x that vanish at the endpoints, then the continuous function m of x must identically vanish everywhere in the integral. We apply this fundamental lemma to our equation. Therefore, we arrive at the condition for which the integral j must be stationary. This is the famous Euler differential equation. Finding the function y of x that satisfies this differential equation is equivalent to finding the path that makes j stationary. Before we move on to generalize this, it is highly convenient to introduce a shorthand. We define the differential quantity del y in the following manner. This represents the infinitesimal departure of the varied paths from correct path at point x and corresponds directly to the virtual displacement introduced in the earlier mechanical treatments. Similarly, we also define the del j as follows. Using the del notation, the assertions that j is stationary for correct paths can be written compactly as following, which directly requires that the integrand satisfies the Euler equation. This del notation is purely convenient shorthand for treating the variation of integrals. Standing in for the rigorous manipulation of parametric families of varied paths we just performed. Armed with this one-dimensional mathematical proof, we now extend it to multi-dimensional spaces and apply it to our physical configuration space. Let us consider a function f that depends on an independent parameter x, a set of n dependent variables y1 of x, y2 of x, such that it goes on till yn of x, and their respective derivatives with respect to x denoted by y1 dot of x, y2 dot of x, and so on. We wish to find a specific set of path yi of x such that they make the integral j stationary. We proceed exactly as before by constructing a parametric families of varied paths. We introduce a parameter alpha that labels a possible set of curves by setting the following. Here yi of x, 0 are solutions to the extremum problem, the correct path we are trying to find. The functions eta I of x are independent functions of x that are completely arbitrary, except they must vanish at fixed endpoints x1 and x2. They must be continuous through the second derivative. The variation of j with respect to parametric alpha is calculated just as before. But now we must apply the multivariable chain rule to differentiate the integral. We sum over all n variables. We yield with the following result for dj by d alpha. We can use the exact same integration by parts trick for second term in the summation because the differentiation with respect to x and alpha commute. Integrating the second term or the second sum by parts yields us the following. Once again, because all curves must pass through the fixed endpoints, the functions eta I, x are arbitrary and are 0 at those fixed points, the partial derivatives vanishes at the boundary, and evaluated first term completely drops out. Substituting this back into our true integral and factoring out the common terms, the condition that the variation del j is 0 becomes the following. Here we have switched back to our convenient del notation. Now we reach a crucial pivotal logical step of the entire derivation. Look closely at this integral. It is the sum of n terms integrated over x. The whole thing must be equal to 0. Because y variables are defined as independent variables, their variations del yi are also completely independent of each other. The arbitrary functions eta 1 of x has no relation to eta 2 of x. Therefore, we cannot rely on positive contribution from one term in the sum cancelling out the negative contribution from another. By obvious extension of the fundamental lemma of the calculus of variation which we discussed, the only way this integral can vanish for any arbitrary set of independent variations del yi is if the coefficient for every del yi vanishes separately. This requires us the following, that it must be 0 for all I equals 1 to n. These are the Euler-Lagrange differential equations. Their solutions represent the curves for which the variation of our multidimensional integral vanishes. Finally, we arrive at the summit. We have complete mathematical structure necessary to translate Hamilton's principle into these equations of motions. We merely need to apply one-to-one translation dictionary from our pure mathematics back into our physical system. Recall, the Hamilton's principle defines the integral I as the following, where the variation of the integral I del I equals 0. Let us map the variables. First, our independent parameter x in the math corresponds to time t in physics. Second, our dependent variable yi corresponds to generalized coordinate qi. Third, the derivative yi dot with respect to x becomes the generalized velocity qi dot. Finally, our arbitrary function is replaced by Lagrangian of the physical system. In deriving the generalized Euler equations, we relied on one absolute critical assumption, that yi variables were independent. The corresponding condition in connections with Hamilton's principle is that the generalized coordinates qi must be independent. This requires that the constraint on our physical system to be holonomic. If the constraints are holonomic, we can always choose set of independent generalized coordinates. Substituting our physical variables into Euler-Lagrange equation, we obtain the Lagrange equations of motion. And there it is, we have accomplished our original aim. We have shown Lagrange's equations follow directly from Hamilton's principle for monogenic systems with holonomic constraints. This is a breathtaking result. The complex vector mechanics of Newton requiring an accounting of all individual forces and constraint acting on every particle has been replaced entirely. By simply finding the scalar, kinetic and potential energies of the system to form the Lagrangian L and inserting into this differential equation or this differential operator, we can systematically generate the complete set of motion for arbitrary complex systems. The entire physical reality of the system's dynamics is now encoded in stationary path of a single integral in configuration space. These are first of my videos, and I would be really happy to know from you guys, what do you feel about them? What are the areas of improvement and what would you want me to do next? Have a good day and hope you have understood. You can ask questions or doubts in the comment sections. All questions are welcomed.